Okay, today is a lecture on lasers, light amplification by stimulated emission of radiation. In the previous lectures, we were talking a lot about Jablonski diagrams, radiative transitions, and figuring all that out and the terminology and understanding how photochemistry works is really important for explaining chemistry, but there's other very practical uses, one of which we're going to talk about today in lasers. And lasers, or laser itself, is an acronym. So sometimes you'll see it written in all capital letters like this, and it stands for light amplification by the stimulated emission of radiation. Okay, so let's break down each of these words. Light. Well, we know what light is. That's great. Amplification means you're taking maybe one photon of light and making 2, then 4, then 8. You're amplifying it. Stimulated emission is something we have to introduce as some terminology. And radiation, well, again, that's maybe a little bit redundant with the word light. So let's talk about types of light or processes that are radiative transitions, like we talked about in previous lectures. And the first is emission. Okay, so emission is the key one here that we're going to use. Of course, we're going to use, as we'll see, absorption as well, but emission is the one we care about. After all, it appears in the acronym for lasers. So emission can come in two varieties. Emission can be spontaneous. And this is so far the one we have talked about in the previous lectures. So we can have spontaneous emission. Okay, this is going to be exactly like it sounds, spontaneous and random. And really depends on the lifetime of the excited state. So you'll remember in previous lectures when we got to talking about photochemistry, Jablonski diagrams, we were relaxing back down in fluorescence or phosphorescence. And the lifetime of phosphorescence is much longer because there's a spin flip versus fluorescence when there is no spin flip. Okay, so spontaneous emission is something like fluorescence where you have this excited state, right? And it's just relaxing back down. And we had lots of diagrams for this, right? So this is your excited state up here. This is your ground state down here. And you're populated up here, so sometimes you draw an electron that's been promoted up here, right? And it's relaxing back down, and when it relaxes, it emits off some wavelength of light, some photon, to get rid of this extra energy. That change in energy corresponds to hc over lambda, this wavelength of light. Okay, so that's what's happening here in this spontaneous emission. One of the differences between spontaneous and stimulated, which we'll get to, is the emission here is in a random direction. It's a random time frame, it's a random direction, right? It's a random phase. So while maybe 2 photons, if there's another electron here that's relaxing, while there can be a second photon, maybe it is emitted in this direction down here. Okay, it's going to have the same wavelength as this one because it's still the same change in energy, but it's going off in a different direction. Okay, and so we call that divergent. Right, the photons here will be emitted in essentially every direction. Okay, but they'll also be incoherent. And incoherent means the following. Maybe there's a third photon that's relaxing, and for this, maybe I'll switch to red so it's more identifiable. This electron that relaxes, well, it emits a photon as well. And maybe it emits a photon in the same direction as this second one did. Okay, so the photon is still going to go down and to the right, sort of southeast here, but instead, it is incoherent. And it's incoherent in the fact that it's not the same exact phase relationship as the first one. Okay, these are now out of phase with each other, That's what incoherent means, right? Different phases. And so those two photons traveling in the same direction will offset and destructively interfere. Okay, so this spontaneous emission is going to have divergent, incoherent light. And an example of this would be a light bulb. Okay, so your light bulb down here, that's giving off all this light in each direction, right? It's really giving off photons in this direction, and photons in this direction, and photons in this direction, and maybe it's giving off different types of photons in this direction down here, but some of them are going in all these different phases, right? So there's incoherent, divergent light from this light bulb. This is supposed to be a light bulb here. It probably looks like something different to you, but that's the best I got. Okay, so that's spontaneous emission. Now, the other type of emission that can happen is the one we're concerned about today, stimulated emission. Okay, this is the second type of emission. It can be stimulated. And stimulated emission occurs when an incident photon triggers a photon emission. And in this case, the incident wavelength matches the necessary wavelength or change in energy of the quantum system. Okay, so let's think about this same sort of diagram. Here's my ground state, here's my excited state. Okay, only if a photon coming in, and now my electron is down here, and now I'm going to talk about, that would have been absorption. It's up here, it's emission. Only a photon coming in that is of the right wavelength that matches this change in energy, can it trigger this electron relaxing? Yes, the electron can relax all on its own, that's true, and emit a photon, but it turns out that process is stimulated if the incident photon wavelength is exactly this quantum difference in energy. Okay, so this photon comes in, it causes this relaxation, and now our system looks like this. Between the ground and the excited state, the electron is now down here. This photon that entered was not absorbed, so it keeps traveling. But this relaxation event gave off a second photon that will be exactly the same in terms of wavelength because it's this same delta energy that is needed. So now, in this stimulated emission process, we have one photon coming in and two photons coming out. Okay, so this is essentially amplification right here. Okay, so you're taking light and amplifying it, light amplification, due to the stimulated emission of radiation. Okay, so that's a laser in a nutshell in terms of all the parts of the acronym. Okay, so one photon in, two photons out. Importantly, right, the emitted photon has the following property. It's the same wavelength, right? Same frequency, whichever you want to refer to, E equals h nu, or E equals hc over lambda, but it's the same energy photon that's coming out. it's going to have the same phase as well. Okay, and for that same phase, well, we call that coherent. Okay, it's going to have the same direction. And it's going to have the same polarization. So basically, every property you can think of for this photon coming out is going to be the same as the photon going in. Now, it's important to note here that any photon coming in doesn't necessarily trigger this event, right? It has to be the particular right type that matches this separation in energy. So only then will you trigger this stimulated emission of another photon, and it'll have exactly the same wavelength, frequency, phase, direction, polarization as the incoming light. Okay, and maybe the way we can think about this is not in a photon picture. That's a little bit classical sometimes, and it's better to think about this in terms of a wave picture. Okay, so imagine, an electromagnetic wave interacting with a molecule. Okay, and we've discussed this before. If you consider, putting a molecule like HCl, where there's a dipole here, and so the H is plus, the chlorine is negative. And now, if you're exposing this to radiation, well, light is really an electromagnetic field, right? There's an E field here, like this, and then it flips so that it's down here. So it's this alternating electromagnetic field that is light. In any case, this electric field of the light will have an effect on these dipoles. So you can imagine putting this between two plates. First, the field is like this, and so there's a net motion of the hydrogen to the right and the chlorine to the left, but then the field switches because light is an alternating electric field, and now there's an induced motion back to the left for the hydrogen and the right for the chlorine, right? Since opposite charges attract here in the second part, now that I've flipped the field. And so you're inducing this motion here. That could be like an absorption event, right? You can absorb the photon or the electromagnetic wave and promote this type of oscillation, okay? That's an induced motion, that's absorption. We've talked about that in previous lectures. Now, you could think of this motion as already being present, okay? This existing motion that has the same field associated with it, because now you have charges that are moving, right? Now light is not prompting this motion, the thing's already moving. So if the charges are already moving, right, it already has an electric field associated with it, and an electric field that is alternating. So if you consider this oscillation of these charges as itself a time-varying electric field, well, now it's probably not so surprising that a passing photon with the same electric field that happens to pass by at the same time with the same alternating electric field, these two could add to each other in phase, right? To create the same kind of larger amplitude wave. Constructive interference between the two, right? So if you're thinking about a wave picture, maybe it looks like this. If it's a photon, it's one photon going in that triggers two photons coming out. Okay, but this is like an electric field being added to in phase, creating a field of twice the amplitude and leaving the molecule now essentially motionless, right? Because you've pulled away that electric field. They've sort of constructively interfered. Right, so that's the wave picture we're going to think about. This is the first photon coming in. This is the existing sort of electric field, and now I get two photons coming out. In other words, one larger electric field with twice the amplitude. Okay, and these two photons have the same phase, which we called coherent. We'll just repeat some of this here. They have the same wavelength, which we call monochromatic. And they have the same direction, which is termed low divergence. And so this is what you'll see a lot of times as, the benefits of laser light. When you get this amplification of light, right? Larger amplitude here now, twice this height. You've amplified the light due to this stimulated emission of radiation, and this laser light has these properties. Lasers are nice because they are coherent, because they're monochromatic, and because they have low divergence. And this low divergence one is the reason you can, shine a laser off the moon and actually see it still being somewhat bright returning to Earth, right? Because the light, from an incandescent light bulb, goes in every direction, well, the intensity falls off quite quickly with radius. But since the laser light is all the same direction, does not diverge, well, if you put a mirror out there with perhaps the mirror is the moon in this case, it'll return at the same angle, and you'll be able to see it back on Earth. Okay, so this low divergence happens to be a key component for using lasers a lot of times. Now, that's sort of the basics and fundamentals of the terminology of lasers. Now we need to jump into sort of our diagram a bit further, like we talked about in the last lecture, and learn something about how to make a laser. Okay? Not every material will be able to laser. And so what materials do laser? How do you make a laser? You have to amplify light. And what really governs whether that's possible or not? So, to make a laser, you need light amplification. Okay? This light amplification part of a laser dictates the following. Okay? Light out greater than light in simple terms. Okay, now if we think about just a simple two-level system like we've been drawing here, between some ground state, we'll call it level 1, and an excited state, we'll call it level 2. Okay, if we want light out to be greater than light in, we probably want to limit absorption. Because if your absorption is too high, then you're pumping too much light into the process, and you can't really get more light out than you're putting in. Okay, so somehow we have to limit absorption here. And what really governs the rate of absorption versus emission? And so let's think about each of these processes. We'll think about first this absorption event. And we'll think about the two types of emission we've talked about here. One of which was spontaneous emission, like fluorescence. And the other was, of course, stimulated emission, the one we need here for lasers. Now, anytime you want to calculate or quantify, something coming out or something going in, whether it's water filling up a bucket with a hole in it and, whether the water level rises or falls, or whether it's reactants to products in a chemical reaction, or there's competing processes here, it's really a matter of kinetics. Right? And kinetics, at least in chemistry, chemical kinetics is about these rates. Okay? And a rate, as we've learned about it in previous lectures and classes in chemistry, is all about some rate constant times a concentration. Okay, so it's not really defined that way. There's a mathematical equation. There we go. So the rate of some chemical process is the rate constant for that process times the concentration of the reactants there. Okay, so in that framework, we can think about this concentration here really as the number of molecules in a given level. Okay, so it's not really a concentration in terms of molarity or moles per liter, but instead this is going to be a number of molecules in a given level. So this number of molecules in a given level. And so we'll refer to this as capital N, the number of molecules, N1 in level 1, for example. Okay, so now we have some idea of what the concentration should be, and we can think about the rates for each of these processes. Okay, the rate for absorption is going to be the following. A rate constant for absorption, which we're going to call beta, and beta is going from level 1 to level 2. It's going to depend on the radiation density, and it's going to depend on, well, the number of particles down here in the first level, N1. So these things sort of together here represent this rate constant, but more specifically, we'll probably just call this beta the rate constant, and rho here is my radiation density. Okay, because there is two things that matter here. It's the light coming in. How many photons are there? What is the density of radiation for that particular wavelength, right? For this particular delta E. What is the radiation density at that energy? And beta here is just the rate constant for the process. N1 is the number of particles down here. Okay, so that's my absorption rate. My stimulated emission rate is going to look somewhat similar. Beta from 2 to 1 times a radiation density. But here the number I need is N2, right? Because I'm starting up here, that's my reactants in this sort of rate constant analogy, right? This is just the concentration always of reactants, not products. So here the reactants is the number of molecules in the level I'm starting with, right? That I'm going to emit from. Okay, so what is the number of molecules with electrons in the excited state up here versus down here? So just the raw number N2 here. That's why it's going into the stimulated emission rate. The spontaneous emission rate then should also have that N2 term in it, and it does. It doesn't care about radiation density, and so we're going to use a different rate constant, A, 2 to 1. Okay, so the spontaneous emission rate doesn't care on the radiation density. Why? Because it's not like light is coming in to trigger spontaneous emission. It's spontaneous, it's all on its own. It doesn't depend on the light like absorption does or stimulated emission does. Okay, so you'll notice here we use sort of the same constant here because the physics is exactly the same, right? B12 or beta 12 equals beta 21. Why? Because, you're just playing the movie in reverse, right? The rate constant for it going up here, given the same radiation density, is exactly the same rate as the reverse process. Okay, so the only difference here between stimulated emission and absorption, and the rates at least, is N2 versus N1. Okay, so if we want the light out to be greater than the light in, what we really need is N2 to be greater than N1. Okay, so again, these are the rates for absorption and stimulated emission. The constants are the same. The radiation density is the same. So how do I get a stimulated emission rate, light out, greater than the light in? Yes, light out also depends on spontaneous emission, but in lasers we'll see that is going to be kind of negligible, this random event that happens, versus the triggered event that we can do. So really, in terms of light out being greater than light in, it's just about how is the rate for stimulated emission bigger than the rate for absorption. Well, here are the two rates. These two terms cancel. They're the same. Those two terms cancel. And so the rate will be greater for stimulated emission than absorption if N2 is greater than N1, and we will have more light out than light in. Okay, so hopefully that makes sense. This N2 greater than N1, number of particles in the excited state, greater than the number of particles in the ground state, we call that a population inversion. Because most of the time, right, in physics, we think things lower their energy. There's going to be more things in the ground state than the excited state. Okay? Lower in energy has a higher population in accordance with Boltzmann distributions, which we've talked about previously. So the real key to lasers here is creating this population inversion. Right? So how do you do that? How do you actually create a population inversion? Okay? The trick is you're not going to have it just between two levels like this, because the ground state is always going to be favored, right? Just because of Boltzmann distributions and temperature. So imagine the following scenario. Imagine a scenario now where you start with the ground state and you cause an absorption event. Okay, and now we're getting back to Jablonski diagrams in the previous lectures. Okay, so here's my absorption. Right, and we're going to use a lot of light here. So we're going to use high intensity, lots of photons of light. So lots of absorption events into the system. Okay, this is called pumping. So in lasers, you often need to pump your system. Okay, so that's step one here, this pumping. Step two is that this excited state that we're now in is going to couple to another state. And if you go back and remember our Jablonski diagrams, you remember that this could be this second process here, could be internal conversion, could be intersystem crossing. Right? But in some case, we're going to probably an excited vibrational or rotational state. Of this other excited state. Okay, so that's step two. You have absorption, you pump a whole bunch of things up here. A lot of them have favorable coupling to this other excited state through internal conversion or intersystem crossing. Then, once you're here, you're going to vibrationally relax down. Draw a few more states here. You're going to vibrationally relax down in process 3. To the lowest rho vibrational state of this excited state. So this is an excited state here. This is a ground state here. This is an excited state here. And step 4 here, and it really should be a vertical arrow, but I'll just, well, we could, I suppose, just make this ground state longer. Step 4 is then to relax back down, right, in an emission event. Now, we can use this sort of electronic structure and these processes, if they're favorable, to set up the following scenario. Rates 1, 2, and 3 are fast compared to 4, and only certain materials will have this capability. Okay, then you can achieve a population inversion. Okay, so you absorb quickly, you intersystem cross quickly, you vibration relax quickly, and then you sit here for a little bit until you emit. And so if 1, 2, and 3 are fast compared to 4, and you're really pumping a lot of light in here, then you're depleting this ground state, and you're depleting this ground state faster than it's being filled by emission. And so you're going to wind up with a net effect of a whole bunch of molecules in this excited state over here, relative to a few down here, and there's your population inversion. This is greater than this. N2 is greater than N1, where 2 is just some excited state and 1 is the ground state. And now that we're inverted, all we have to do, which is beautiful, is wait for 4 to emit. And when 4 emits, maybe it emits a photon this direction, and the wavelength it emits, well, will be characteristic of this energy separation. And now imagine we put a mirror over here. That's not a mirror, we'll just go like this. This is a mirror. Well, now this photon that's been emitted collides with the mirror, and now it goes back this way. And when it gets to here and sees this certain energy that it's matching, well, these excited state molecules, for the reasons we just went over back here, will couple to this photon and emit 2 photons out. And they'll have exactly the same phase. And now you put a mirror over here on the other side of your cavity. So 1 photon that we've captured and reflected back towards this solid medium or gaseous medium becomes 2 photons, and the mirror over here sends it back, and those 2 become 4. And the 4 bounce off here and come back and become 8, and so on and so forth. And now we're amplifying things. And to put it in a more sort of practical sense, all this solid and all those, well, it doesn't have to be a solid, but all those electronic levels, right, are in this solid that we just call our lasing medium, right? The thing that has that electronic structure set up in such a way. Okay, it could be ruby, that was the first laser. It could be neodymium, yttrium, aluminum, garnet, neodymium YAG lasers, very popular. But whatever it is, here's the medium. And so we pump all of this, use a very bright, high-intensity source over here. Doesn't have to be, and in fact shouldn't be, this separation of energy, but it is this separation of energy for the pump. And so we pump it with really bright light. It is now excited. It is undergoing intersystem crossing and vibrational relaxation, and eventually, 1 photon comes spitting out over here, and we capture it off the mirror, and now we have 1 photon coming back here, and this 1 photon going in becomes 2 photons going out, and this 2 photons going out, well, hit this mirror on the other side of our cavity and become 2 photons going back this way, and the 2 photons going back this way become 4 photons coming out on this side. And then 4 becomes 8, 8 becomes 16, so on and so forth. Okay, so you're taking even broadband light down here. It doesn't have to be the exact absorption as I showed on the previous slide, but it can be broadband, many wavelengths, as long as those wavelengths are, short enough to promote this excitation or greater. There could be other excited states. You're going up here till vibration relaxing before you start all of this. That's possible too. Or you can have not just 3 levels that's shown here, 1, 2, 3, but you can have a 4-level system. That's pretty common in lasers as well. Okay, but this is all you do. You take broadband light and pump the lasing medium. You set up this population inversion. 1 photon gets emitted, that becomes 2, that becomes 4, so on and so forth. Okay, so you just have to put a material with these good energy levels that are conductive or conducive to a population inversion. Use some mirrors, and at the end you'll have a bunch of collimated, monochromatic, low divergence light. And then once you get up to a certain amount of light, you remove this mirror or turn on some other mirror or find some way to get the light out of the cavity. And so you dump all the light out at once if you want a pulsed laser, or you use a sort of transparent mirror to slowly leak out some of the light if you want a continuous laser. Okay, so that's the simple operation in terms of the electronic structure of a lasing medium and how you actually set up something that will laze and capture this monochromatic, low divergent, coherent light source and use it for some application. So that'll do it for this lecture on lasers. In future lectures, we'll start to understand a little bit more about electronic structure of molecules, going into molecular term symbols, and what kind of transitions are favored and not favored in molecules, which explain things like ozone in the atmosphere and the absorption of light by oxygen, and climate change, amongst other things. So look forward to those lectures next time. That's it for this video.